In this video, we are going to go over the perpendicular bisector theorem. Let's go over what a perpendicular bisector is. A perpendicular bisector is a line segment array that intersects the midpoint of a segment and is perpendicular to that same segment. Let me illustrate this for you. Here you can see that XY is the perpendicular bisector of the segment AB. Because it intersects at the midpoint of AB, let's name this point P, and when it intersects, it is perpendicular to the segment. So XY is the perpendicular bisector. Let's go over the perpendicular bisector theorem. The perpendicular bisector theorem, T27, says that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of that segment. So what we're going to have to prove is that this point X is the same distance from A as it is from B. So X is our point on the perpendicular bisector, so it has to be the same distance to A and B, the endpoints of the segment. So let's go ahead and do a two-column proof. First of all, from the theorem, we're given that XY is perpendicular to AB, and XY, the line, bisects the segment AB. And we have that point P is the midpoint of AB by the definition of the perpendicular bisector. Since P is the point where line XY intersects segment AB, since XY is the perpendicular bisector, then P is the midpoint of AB. And we know by the midpoint theorem that AP is congruent to BP, because P is the midpoint between those two endpoints. Therefore, AP is congruent to BP. And we know, since XY is perpendicular to AB, that this angle APX and this angle BPX are both 90 degrees and therefore are congruent. And that's because of the definition of a perpendicular line. Now we can say that this segment PX is congruent to the segment PX. And that's by the reflexive property of congruent segments. So if you see, we have created two triangles, triangle APX and triangle BPX, and because the side angle side is congruent to the corresponding side angle side, then the two triangles are congruent. And we know that when two triangles are congruent, then their corresponding parts are congruent. So that means this side, AX, is congruent to the side, BX. And since those two are congruent, they're equal in measure. So AX equals BX by the definition of congruence. And that's what we needed to prove, that given some point on a perpendicular bisector, then that point is equidistant from the endpoints of the segment that perpendicular bisector is intersecting. The perpendicular bisector theorem. So this is the proof to the perpendicular bisector theorem. Let's go over the converse of the perpendicular bisector theorem. So the converse of the perpendicular bisector theorem, T28, starts with the conclusion of the perpendicular bisector theorem and then implies the hypothesis. So if a point is the same distance or equidistance from both the endpoints, so that was our A and B, then it lies on the perpendicular bisector of that segment. So that could have been our point X on the perpendicular bisector XY. We have a new definition, concurrent lines. Concurrent lines are three or more lines that intersect at a common point. Here I've drawn three different lines, and they all intersect at this common point. That common point is known as the point of concurrency. So that point where the three lines intersect is the point of concurrency. Let's think about concurrent lines in the form of perpendicular bisectors among triangles. So let's say I have some triangle A, B, C, and each segment AB, BC, and AC have a perpendicular bisector. So I have three perpendicular bisectors, X, Y, and Z. The point at which those three perpendicular bisectors intersect is known as the circumcenter. So a circumcenter on a triangle is where each of the segments has a perpendicular bisector, and those three perpendicular bisectors intersect at that one given point, known as the circumcenter. And there is actually a theorem dealing with the circumcenter of a triangle. The Circumcenter Theorem, T29, says that the circumcenter of a triangle is equidistant from the vertices of the triangle. Let's think about what that's saying. Here we have our circumcenter. This theorem says that vertex A is the same distance to the circumcenter as vertex B is, as well as vertex C. So it's saying that line A to the circumcenter, if we name the circumcenter P, A to P is the same distance as B to P, which is the same distance as C to P. So those are all congruent. I'm not going to prove this in this video, but let's think about how we would do a proof. By the perpendicular bisector theorem, we know that if a point is on a perpendicular bisector, then it is equidistant to the endpoints. So since P is on the perpendicular bisector of BC, then B to P must be equal to C to P. And P also lies on the perpendicular bisector Z, which bisects AC. So that would mean A to P is the same distance as C to P. And then you would just use the transitive property or substitution to say that B to P is equal to C to P, which is equal to A to P. In this video, we went over the perpendicular bisector theorem and then applied that theorem to prove the circumcenter theorem.